Today we're going to prove something called the stability theorem. The basic idea is, so I'll write a specific statement in a second, but so imagine G has no KR and has close to EX and KR edges, where n is the number of vertices in the graph. Then what we want to show is that basically then the structure of G is close to an extremal example. Extremal example, I mean just a complete R minus 1 partite graph. Right? So this is it's a kind of a different sort of thing. We've been doing mostly supersaturation, which says if your number of edges is much bigger than this number, or maybe with an H, then you have a lot of copies of H. This is kind of a different topic where, so now we're going to have the number of edges of H is going to be below the extremal number, but close to it. And then you want to say, and it has no KR. And then you want to say that it's got to look kind of like one of these constructions. So there's different sort of versions of this statement. I'm going to prove one today that's I think quite elegant and nice. So this was first so this specific statement was proved by Fioretti, I think in like the early 2010s or something. So the statement is as follows. So let n be at least r, which is at least 3. And let's say t is at least 0. The parameter t is going to kind of represent how close we are to the extremal number of edges. So if G is a KR free, meaning there's no copy of KR, graph with at least, with n vertices, and at least extremal number of KR minus T edges, so this is meaning we're quite close to the extremal number, then there exists an edge set E1, which is a subset of the edges of G, and a set E2 of edges, which is in the edge set of the complement of G. Remember, the complement is the graph where you take the same vertex set as G and you put every non-edge of G becomes an edge of the complement. So such that if I take G, I take away the edges of E1, and I add in the edges of E2, I get a complete R minus 1 partite graph. And there's not too many edges so that we're deleting. So the union of E1 and E2 is at most 3 times t. Okay, kind of a long statement. Let you kind of digest that. Yeah. That's actually a really good question. Yeah, so in some sense, because remember, yeah, our real extremal example is R minus one part height, and all the parts have like the same, roughly the same size, right? I'm not going to claim that here, that the parts have roughly the same size. So in some sense, yeah, in some sense, this is not really showing that we're close to the extremal example, but yeah, you can kind of build on this theorem and get that, like, under certain conditions, you're close to the one where they're all the same size. But yeah, we're just going to get to some R minus one part height graph, and we won't have any guarantee on what the part sizes are. That's a good question, yeah. Any other questions? So yeah, is it clear what this is saying? We want to say, yeah. I mean, this is kind of our notion of being close to a kind of extremal example, although not exactly extremal, right? If I basically add and remove 3 times t edges, you'll get to a complete R minus one part height graph. Okay. Okay, so let's prove this. So the first step of the proof actually is to observe that finding the set E2 is not actually that important. Like, we're kind of going to focus on finding this set E1. And in some sense, we'll get E2 for free. So, I mean, if you think about it, what do I want? What role does the set E1 play? Like, these are edges I'm removing from G. If I remove those edges, I want the graph to be R minus one part height, not necessarily complete, right? So I want to remove these edges to make it R minus one part, like chromatic number at most R minus one. And then what am I going to do with A2? Well, I'm just going to, like any missing edges between the parts, I'm just going to add them, right? It's kind of clear, once I've removed the edges of E1, it's kind of clear what to do with E2. Just complete the parts to make them complete, right? So all we really want to do, so our goal is to find a set E1 in the edge set of G such that, so when I'm talking about part height, like, I mean, really we care, I mean, so the chromatic number of G minus E1 is at most R minus 1. And the size of E1 is at most T. Now I claim that this is sufficient. So so once we do this, so if we can find this set that has those properties, let E2 be the set of all kind of missing edges between the kind of color classes. So when I say color classes, I mean kind of color this graph with R minus 1 colors, and then so basically what I want to claim is that if I can guarantee that E1 has size at most T, then this E2 will be guaranteed to have size at most 2T. And that'll give me my bound on E1 and E2. Okay. So I claim we're going to get that the size of if we do this, if I manage to do this, where E1 has size at most t, this E2 is going to be guaranteed to have size at most 2t. The reason is as follows. When we started, how many edges did we have? Extremal number minus t. If this E1 exists, then I delete an additional t edges. And now let's say I add the edges between the parts. And suppose that somehow that was, so at the moment, after deleting E1, I've got extremal number minus 2t edges. Fill in the edges between the parts. And suppose that added more than 2t edges. I'd be above the extremal number, but it's r minus 1 partite. Like, that just can't, you can't have an r minus 1 part, because then it would have no kr and it'd have more than the extremal number of edges. So just to kind of formalize that, so claim, my claim is that, yeah, the size of E2 will be at most 2t. Otherwise, so here's the proof. If I, G minus, the graph G minus E1 union E2 has no kr and has at least extremal number minus E1 plus E2, minus t minus E1 plus E2 edges. So if E1 is at most t and E2 is bigger than 2t, this contradicts the definition of the extremal number. Okay, so that was kind of quick, but I kind of explained that in words before. So, yeah. So basically our goal is to find E1, and then the definition of E2 is kind of clear. You just need to fill in the edges. And there couldn't be that many edges to fill in because we started close to the extremal number and we only deleted a little bit. So you can't go above the extremal number, right? Without containing a kr. Okay. Okay. Now, finding this set E1 of edges, it's kind of the same thing as, so I want to delete those edges to make it r minus 1 partite or chromatic number at most r minus 1. That's the same as like finding a partition of the vertices into r minus 1 sets such that inside the sets there aren't very many edges. Because then the edges inside the sets are the ones I would delete. So basically our goal is to find a partition of G, of the vertices of G, although it's maybe not technically a partition. I'll allow some of these sets to be empty but yeah, so these sets are going to be disjoint, but they could be empty. So maybe I'll put this in quotes. I don't know if partitions have to have non-empty sets or not, but so sets, so the VI could be empty, but they have to, so they're disjoint and they cover the vertex set such that the sum I equals 1 to r minus 1. So I'm going to use this notation to mean, so e little e vi, I'm going to use this to mean number of edges inside the set vi. And I want that to be at most t. And then I just defined E1. I'll just define E1 to be like the edges inside V1, V2, like the edges inside any of these sets. So is it clear that this is what would this is what we want basically? Okay. Okay, so we're going to do something. It's actually kind of, it feels to me, well, like kind of, it's sort of spiritually kind of related to what you're doing on the first question for assignment 3, which I think is due tonight, right? But this idea of taking a biggest vertex in a graph with no KR and like recursing sort of on the neighborhood of that vertex or something. We're going to basically do, like, we're going to run some sort of algorithm starting with the biggest degree vertex, recursing in the neighborhood and stuff like that. But we're going to, like, we're not going to use induction kind of like you do on the assignment. We need to really carefully count edges. So yeah, we're going to kind of describe the whole algorithm rather than just doing like an inductive step. But so we construct, so we follow, we use something called the Erdős degree majorization algorithm. Okay, but I'm pretty sure this is very similar to what would just happen if you just went through that inductive proof on your assignment and then, but didn't do induction and just followed it all the way through. So here's the description. So I'm going to initialize, before we start the algorithm, I'll define a set V0 plus to be the set of all vertices of G. Yeah, you should think of this set as like the set of vertices that haven't been processed yet, and then we're going to process them later. So for each I at least 1, do the following. Well, if there are no more vertices that we need to process, then we just stop. So if vi minus 1 plus is empty, that means we've already processed everything. Just stop and output the partition. Well, it's going to end up being a partition v1 up to vi minus 1 with enough, if I is less than r, then so you've got like r minus I empty sets at the end of the partition. I mean, yeah. if we need, because I want to find R minus 1 sets, but anyway. So otherwise, so initially, like V0 is everything, so yeah, it's not empty. Otherwise, we do kind of like what you do on your assignment. Pick a biggest degree vertex and kind of divide the graph into its neighborhood and its non-neighborhood and do something differently in both. So pick, let's say, xi in vi minus 1 plus with biggest neighborhood within vi minus 1 plus. So the neighborhood of xi intersect this set as big as possible. Okay. And then define vi plus to be vi minus 1 intersect the neighborhood of xi, and vi to be, oh sorry, that should have been a plus. So vi plus is vi minus 1 plus intersection neighborhood of xi, and vi is everything else. So vi minus 1 plus, take away vi plus. Okay. One thing to note is that xi is in vi because xi is not a neighbor of itself. So the size of vi plus is less than, so like the set of unprocessed vertices keeps shrinking as we go. Let me maybe draw a picture. So at the beginning of the algorithm, we've got the set V0 plus, which is everything. Maybe I need a bigger picture. First step, we check, okay, is this empty? It's not. We pick a biggest degree vertex. That's x1. And then take its neighborhood and its non-neighborhood. Well, so the neighborhood of x1 will be v1 plus, and the non-neighborhood of x1 will be v1. And that's my first set in the partition, right? So my output is going to be like v1, v2, etc. This kind of makes sense. If you ran this algorithm on a Turán, like a R-1 partite graph, if you pick a biggest degree vertex and I take its non-neighbors, that will be the part that contains that vertex. So this will, like, if you were in a complete R-1 partite graph, this would basically select a part and then select another part of the R-1 partite graph. And then, yeah, inside of V1, we pick an x2. Sorry, inside of V1 plus. So this is V1, the non-neighbors, which includes, actually, V1 includes x1 as well. And yeah, we pick a biggest degree vertex, look at its neighborhood. That's V2 plus. And its non-neighborhood, which includes itself, would be V2. And then we just keep tunneling inside the neighborhoods. Okay. And now I claim that this partition has the properties that we want. One problem is like, what if this partition has more than r minus 1 parts? That could be a bit of an issue. In some sense, that this would be kind of not well defined. But it can't, because this graph doesn't have any KRs. So here's the thing. In this picture, like if I look, x1, like where was x2 chosen? It was in the neighborhood of x1, because that's v1 plus. So x1 and x2 are adjacent. And then x3 was chosen within the neighborhood of x2, kind of within the neighborhood of x1. So x2 is going to be, or x3 is going to be adjacent to x2, as well as x1, because it's in like the intersections of their neighborhoods. So in fact, all of these x vertices make a clique. So x1, x2, like all of the, all of them make a, so for any I for which the algorithm is still running, form a clique. So a complete subgraph. Okay, and since G has no KR, the algorithm must terminate after at most r minus 1 steps. So I guess it terminates before, like, yeah, or after at most r minus 1 steps. By which I mean, like, it could not have constructed a vertex XR and a set VR, because, yeah, they'd make a clique. Okay, so this does output like a partition into r minus 1 sets, because some of them might be empty. Okay. Oh, also, is it clear that this is a partition, that like these sets are not going to be, they're not going to intersect? Like if you think about it, in our first step, if I take v1 and v1 plus, that partitions the vertices into 2 sets. It's the neighbors and the non-neighbors of the first of x1. Because remember, x1 itself is in v1. And then, like, as I recurse this algorithm within v1 plus, like the next step just partitions v1 plus into 2 sets, like v2 as well as the unprocessed vertices. And then this just the next step just partitions this into 2 sets, and so on and so forth. So at the end, like, once I get that vi minus 1 plus is empty, like the vi's will, will partition the vertices. So all we need to show is this inequality, that there aren't too many edges inside these sets. Is that clear, or any questions about that? So this, I guess I'm claiming this is a partition, and there are only r minus 1 sets in the partition. So they're not, these are disjoint sets. Okay. So yeah, what we want to show is there are not too many edges inside the parts. Okay. So for each index, suppose I count, so I'm going to go over all the vertices in VI and count the number of neighbors of V within VI minus 1 plus. Okay. So if we kind of just think of this as like our whole kind of, the whole kind of universe at this point is just VI minus 1 plus, which at the beginning of the algorithm, like if I is 1, this would just be the whole graph. But now we're, like this is the stuff that's not processed so far. And take something in VI. So like the whole, like VI minus 1 plus is partitioned into these two sets. It's either, everything's either in VI or VI plus. Because this is the neighborhood of Xi, this is the non-neighborhood of Xi. So all I'm claiming is that this counts every edge inside of this set twice. And it counts the edges between VI and VI plus once. So the notation I'll use for this is like E VI VI plus, and this is the number of edges from VI to VI plus. Like, so number of edges with one endpoint in each set. Okay. Is it clear? Like, this is just handshaking. Any edge that lives inside of VI is going to be counted twice from either endpoint. Any edge that goes from VI to VI plus will be counted once. The edges inside of here will be counted 0 times. Okay. So there's just kind of a double counting. I can also say that by definition of my vertex Xi, that this is at most, so for each vertex V, like this, by the way I chose Xi, this is maximized when V is equal to Xi, right? Because yeah, that's how I picked Xi to have the biggest such thing. Oh, sorry. But this can be rewritten as that. Because in fact, the definition of VI plus is it is the neighbors of Xi within VI minus 1 plus. Right, from that. Okay. This is really an exercise in a lot of double counting and stuff like that. But are these two, this inequality and this equality, are these clear or? Okay. So yeah, so this is equal to this, which is at most this. So let's sum this up over all of the indices I. And actually, let's notice something that, so VI plus is literally equal to, for any I, so let's take I between 1 and R minus 2 maybe. Well, no, r minus, we can write r minus 1. So vi plus, I guess one reason for this notation, so these are the vertices that have not been processed yet when we're doing step I. So like, and it turns out that that is the union over all j from I plus 1 to r minus 1 vj. Right, because, yeah, these are the vertices that have not been put in any partition class yet, and then they will be put into those partition classes later, like at step j for some j that's higher than I. So, so this quantity here, I can write as it's vi times the sum from j is I plus 1 up to r minus 1 of vj. Right, because this union is disjoint, right, because this is a partition. Okay. So here's where there's like a really kind of cool observation. It's I think quite clever. So, so let's sum over all I. So I'm going to sum this quantity over all I, which is the same as summing this thing. So, so 2e of vi plus number of edges from vi to vi plus, well, which is, by the way, so since vi plus is all the later vj's, like this is equal to the sum j equals I plus 1 to r minus 1 of number of edges from vi to vj. So I'm just saying that's the same as counting this. Right, because every edge from vi to vi plus goes to some vj, like some later vj, right? This thing is kind of partitioned into all the later vj's, and so yeah, that edge must go to one of them, right? So if I take this inequality, what I get is that so that's equal to this sum here, which is at most this number, right? And we're summing this over all I. So, yeah. So the right-hand side, if you think about it, so this is just the sum over all I. I mean, this is just going to be if I match, I take the parts v1 up to vr minus 1, and I just put a complete multipartite graph between them. This is how many edges you would get, right? Because this is like taking from the first part, you'd have edges from the first part to the second part, first part to the third part, and like you'd have v1 times v2 such edges for the first to the second, first to the third would be v1 times v3, and so on and so forth. So this right-hand side is equal to the number of edges in a complete multipartite graph with parts v1 up to vr minus 1, which is at most the extremal number of kr. Okay, and the left-hand side, so the right-hand side is at most the extremal number of kr. Left-hand side, I claim is equal to the, so it's the sum overall, I equals 1 to r minus 1 of the number of edges in vi plus the number of edges of g. So I guess what I'm saying here is I'm claiming this sum counts every edge of G once, except for the edges within VI, which get counted twice. And that's true, right? So every edge of G either goes between two VIs, VI and VJ for some I and J, or it's inside of VI. The edges inside of some VI get counted twice because there's a 2. If you have any edge from a VI to a VJ, and without us generally I is less than J, it gets counted here once. So this will count, for example, the edges from V1 to V2, V1 to V3, etc., V2 to V3, etc., exactly once. And this is counting the edges inside of VI twice. So the left-hand side is equal to all the edges except for the ones that we've double counted, which I've accounted for here. And then we can plug in, this is the extremal number. So this is the sum I equals 1 to r minus 1, edges inside of VI. Remember we had this, well, a lower bound, that this is EX and KR minus T. So now, so this is at most this. We just cancel the extremal number. Okay. And then the edges inside of the sets VI become the set E1 of edges we want to delete. Okay, so it's like kind of a clever algorithm, which, I mean, although it is quite linked to what you've already done in the assignment. And then like carefully counting edges, and then it just kind of comes out. Any questions about any of that? So yeah, this topic is, so stability theorems are like extremely valuable in extremal combinatorics. We're not really going to see any applications of this, but just to let you know, there are a lot of applications of this kind of statement where you say, if you're close to the extremal value, then you're close to the extremal example. But yeah, like I said, we're not going to really see any applications. It's just kind of a nice thing. By the way, also, this gives you another proof of Turán's theorem, because if t is 0, then you are 0 edges away from a complete multipartite graph.